In this video, we're going to talk about some properties of the definite integral. So you know you have a definite integral when you have limits on that integrand, and they're going to be numeric. They're going to be numbers. So it could be from 1 to 4, it could be 0 to 2, or it could be -3 to -1. Either way, you're going to have some kind of limit. So here's what's going on. We're going to have some kind of function, f of x. Maybe f of x looks like this. And what we're doing is we're integrating between two specific x values. I'm going to call this A, I'm going to call this B. And we are trying to find that area under the curve. And what that means is actually the area between the curve and the x-axis. So in this case, it would be that shaded area between A and B. Now, we talked about left sums and right sums, and we said we could approximate that area using rectangles. There's other approaches that we could use too, but we're just going to talk about the rectangles right now. And that's going to lead us to what's called the fundamental theorem of calculus in the next section in 5.5. But let's talk about some properties. So notice that area in this picture lies above the x-axis. So if we get something that's above the x-axis, and then what that means is we're going to end up with a positive number. If the area is below the x-axis, so suppose this graph did something like this, and maybe I have a C value and a D value here. Now I'm looking at a different area under the curve, which really means between the curve and the x-axis. I'm not sure why calculus textbooks say under the curve instead of between the curve and the x-axis, but they do. Notice that area is underneath the x-axis. It's below the x-axis. And when that happens, then when you integrate, you're going to get a value that's a negative number. And all that means is that that lives below the x-axis. Okay, so numerically you would get out a negative. If they're giving you a problem in a book or on My Math Lab or wherever you would see this, they may tell you that area is this number. Area is always thought of as a positive number, but the negative just tells you where it lives. It's like when you talk about other problems. Like velocity. Velocity could be positive or negative. Positive tells you you're going in a positive direction. Negative tells you you're going in a negative direction. So it just tells you a direction there and where it lives. So let's look at some properties here. Now, if we're integrating from A to A, think about what that picture would look like. There really wouldn't be a rectangle there. If we think about this in terms of rectangles, I'm integrating from A to A here. That lower bound and that upper bound are the same thing. So the width of that rectangle would be 0. So wouldn't it make sense that if there's no rectangle, the width would be 0, then there couldn't be an area under the curve. Well, that's what that first property is saying here, is that the area would end up being 0 under the curve. Let's look at the second property. We're integrating from A to B. If we flip those integral limits, it happens to change the sign of the outcome. So if we know A to B is one thing, then if we change it from B to A, going from B to A, we always talk about in terms of the lower bound and the upper bound, then it would change the sign of the outcome. We have a constant property. If we're integrating from A to B of k, which is some constant times a function, we could pull that constant out and then integrate. So if I know this, then to figure out the constant multiple, I would just multiply the constant times that value together. We also have a sum and difference property. If I'm integrating from A to B of f of x plus g of x, I can integrate each piece separately. Notice I'm using A and B as the limits on both. And then the last property, if I'm integrating from A to B of f of x, I could split that up into two different pieces. So for instance, if I have a picture that looks like this, maybe this is A to B, and this is C. Maybe I already know this piece. Maybe this is something that's difficult to integrate, and I already know part of this. Then if I want to know the total area from here to here, looking at both of those shaded regions, if I already know the first one, then all I would have to do is figure out the second one. So you can split that up into two different pieces to integrate. So what I want to do is look at an example. We're not going to talk about where those areas are coming from yet. That's going to come in the next section. But suppose we have this picture. And in this picture, we know some areas. I know the area between A and B, which is area A, is 2. I know the area between B and 0, which lives underneath the graph. Notice they gave it to me in terms of a positive. So they're telling me the area, but they didn't tell me where it lives. I have to figure that out by looking at the picture. Notice they tell me from 0 to C has an area of 4.5. And notice D is an area of 1. And they're just going to ask us to find a few things. So let's play around with some of these ideas. So suppose I want to know what the integral is from 0 to C of f of x. Well, 0 to C would be this piece, so that would be area C, and that value of that integral would be that area of 4.5. It lives above the x-axis. It would be a positive value for that outcome. Now, what if I want to know the value from C to D of f of x? Let me write the dx's in here to be formative. So C to D would be this piece of the picture. Now notice that lives below the x-axis, but the area inside of there is 1. So our answer has to be a negative number because it lives below the x-axis. Maybe I want to know what's happening between B and D of f of x. Well, B to D would be everything in here. So this is where you're going to want to use that property that you can split this up. So we could talk about what's happening from B to 0, which would be just that first piece. And then we could talk about what's happening from 0 to C, which would be this piece. And then we can talk about what's happening from C to D. So from 0 to B, notice that lives below the x-axis. So that area is 1.5, but that value would be negative 1.5. Just because where it lives, it has to be negative. The area from 0 to C lives above the x-axis, which means it's going to be the positive 4.5 value. And then from C to D, once again, we are below the x-axis. That area is 1, but the value of the integral is going to be a negative 1. So if I want that total area, it takes into account where it lives, whether it's above or below the x-axis. So I'm just going to add negative 1.5 plus 4.5 minus 1 gives me a value of 2. So that total area, taken into account where some's positive and some's negative, that value of that integral would be 2. Let's do one more. What if I ask you the area from B to A of f of x? Well, B to A would be this little piece in here. But notice they're reading this backwards. This is where we're going to use that property that we're going to change the limits so it matches our picture. But when I do that, it changes the sign. It's one of our properties. So let's talk about what is the integral from A to B. Well, it lives above the x-axis and it's area A, so that value has to be a positive 2, which means that if I flip those limits, because that's what they asked me about in the beginning, my final answer would be a negative 2. So it's all about where it lives and how can I use those properties. Now let's talk about another set of problems. Suppose I had some information. Suppose I knew that if I integrated from 1 to 4 of x dx, I would get 7.5. Suppose that I knew if I integrated x squared from 1 to 4, I would get 21. And suppose I knew that if I integrated x squared from 4 to 5, I'd get 63 over 3. Now, we'll talk about where that comes from in the next section. But right now, I just want to play with some of the properties. So let's look at an example. What if I asked you that if you knew this information, could you tell me what this is? Well, we can use those properties that we talked about to help us do that. We could pull the 2 out. And then this is something we already know. We know that's 7.5. So we can just take 2 times 7.5 to get that final answer. So we can use the properties to help us figure that out. Now suppose I want to know something a little bit more interesting. What if I want to know the integral from 1 to 4 of 5x plus x squared dx? Well, I can use those properties. I could rewrite this as 5x dx plus x squared dx. And that is the same thing as 5 times the integral of 1 to 4 of x dx plus the integral of 1 to 4 of x squared dx. Now let's substitute in what we know. We know this is 7.5 because they told us that up here. We also know that 1 to 4 of x squared dx is 21. So if we compute this, that will tell me the value of that. And I got 58.5. And then let's do one more. Suppose we want to know from 1 to 5 of 6x squared dx. You could pull that 6 out. Now we don't have a 1 to 5, but we do have a 1 to 4 and a 4 to 5. So we could rewrite that as the integral of 1 to 4 of x squared dx plus the integral of 4 to 5 of x squared dx. We know 1 to 4 is 21. And we know 4 to 5 is 61 thirds. So let's compute this. I got 248, so there's my final answer. Just for fun, let's do one more. Let's do one like this. So first off, you notice that the limits are kind of messed up, right? But we can change that by flipping the signs. Now, also notice that I don't have a multiplication property. But if I distribute, then I'll be able to use the information that I have. So this would be x minus x squared dx. So I could rewrite this going from 1 to 4 of x dx minus 1 to 4 of x squared dx. Okay, notice that negative is still out front. And now we've written it into a way that we know some information. When I integrate 1 to 4 of x dx, that was 7.5. And when I integrate x squared from 1 to 4, I get 21. 7.5 minus 21 is negative 13.5. And if I take the negative of that, I get 13.5. So there's our final answer.